Start recording. Okay, looks good. So whenever you're ready, take it away.
Yeah. Okay. Hello. Thank you, as always, to Greg for the opportunity to present here and for the platform. I will begin by just following the definition of the surface. So today, the surface will be uh, want it to be have a countable basis, unlike Joe Biden, and we want it to be locally Euclidean. So I'm listing these properties explicitly because, as we'll see in a moment, it's not quite as clear when you start talking about infinite type surfaces which of them actually are surfaces, and what kind of things you're allowed to do and what kind of things you're not. So okay, so finite type surfaces are finite type. So finite type will mean phi one fundamental group of the surface is finitely generated. And so we will say that the surface is infinite type if this does not hold. Okay, so let's talk about some examples. So the first example of an infinite type surface you'll see is called the Loch Ness Monster. And this is the surface that I have drawn on the opening slide. So we have genus it's going off and off and off in one direction, and it's closed at the other end. So this is what people will sometimes call the infinite genus surface, or the connected sum of infinite domain torus. This is called the Loch Ness Monster. And then a different example would be the fluid surface. So that is what happens when you take a sphere and you puncture it countably many times, and you have one of the punctures accumulating to, like you have like the natural numbers with the punctures accumulating to a single puncture. This is a sphere punctured with the extended natural numbers. Um, for example, the Cantor tree. So it looks kind of like this. You have first you split up into 2, and then you split up into 4, and then you split into 8. And you continue this splitting up to infinity. And the reason why this is called the Cantor tree is because this is equivalent to R2 minus a Cantor set. Or actually, I think I want a sphere minus a Cantor set. S2 plus C.
Is this a strange one that was depicted in the big set of notes that you sent? There was some artist's rendition of something. Is this that one?
No, no, no. I think what you're thinking of is the genetically modified Cantor tree, which is considerably weirder than this one.
Ah, I see.
So yeah, so this is the Cantor tree. Okay, so yeah, these are examples of infinite type surfaces, and now I will give you some non-examples because initially it can seem like these can just be as crazy as you want, but there are some limitations. So something which is not countable genus.
Right. Yeah, this was my question from the 5-minute preview. So did you say the uncountable genus violates something like it doesn't have a countable basis anymore or something? There was some pathology, I think you said.
Right, right, right. So the problem here is that each genus, like, well, okay, it's not entirely well defined what this means, but I think like what you would I think it to mean would be like a sphere with uncountably many handles or a connected sum of uncountably many tori. And the issue with that is for each kind of segment that we consider to be a quote genus that look like this. Um, these are like you can basically split it up into disjoint segments like this, and each of these segments, which consists of the quote genus, has to contain a basis element, of course. And so if there were uncountably many of these segments, which we call like genuses, then you'd have uncountably many basis elements, which is violates our definition here, countable basis. So, um,
Oh, good. So you would say that any putative surface with uncountable genus is actually not second countable and therefore not a surface. Am I
yes, it's not a
mistaken?
manifold.
Okay.
Yep. So we would say, oh my god. Sorry, this is not. Oh, there we go. Okay.
Something strange seems to have happened on the right.
Well, yeah, because I kept trying to draw X's, but they were not rendering everything. Okay, so what we want to say is that this is not allowed because this no basis. So another way that you can fail to be a surface is if you have functors which kind of accumulate to nothing. So this would be so this is like uh, lack of limit points, I guess you could call it in some sense. So what I mean would be something like this. You took here, and then you said, okay, I'm going to have a puncture here, and then a puncture here, and a puncture here, and a puncture here, and a puncture here, and you're accumulating to something, but the point to which these punctures accumulate is not a puncture. So if you actually had a like if you had a sort of point on the surface here, say, um, then this point would not be like no neighborhood at this point would be isomorphic to R2 because every neighborhood, by definition of accumulation, would contain a puncture. So this is not a manifold because it is not a Euclidean. Okay. These are surfaces, and these are not. Any questions about what kind of things are allowed, what kind of things aren't.
No serious questions. I have a speculative question that you probably won't like, but we were talking about this a little bit in the preview when you got disconnected. So if I don't know how to make this precise because I don't know how to define a measure on the space of surfaces, but if you imagine that there was such a thing, a measure that tells you in the space of all possible surfaces.
Okay, yeah.
Yeah, I mean, would you expect that infinite type surfaces are in some sense generic, or that the finite type
Absolutely.
surfaces are a set of measure zero? Is there some
Absolutely.
indication?
We will see that there are uncountably many infinite type surfaces of the homeomorphism, whereas there are only countably many finite type surfaces of the homeomorphism. So absolutely,
Okay.
it would be a set of measure zero. And in fact, we like this will make sense later, but the set of subsets of the Cantor set, which can comprise n spaces of finite type surfaces, I think is literally. Oh well, never mind. The answer in some sense is yes, but we'll talk more later about that. Okay, so and actually, I think that's what we'll talk about next. So we want to talk about n's. We're going to fix a compact exhaustion, whether it's like an exhaustion of finite type subsurfaces of sigma. So we'll let sigma equal 1 union S2 union dot, where S1 is contained in S2 on and on. These are all finite type. And so you can imagine this is our surface. You have like the genus here, and a genus here. And maybe some splitting. Then this would look something like this. So here is S1. And then here might be S2. It might be S2. And you continue getting bigger like this. So this is called an exhaustion by finite type subsurfaces. And so given that we have like fixed one of these, then we say that an end of sigma is twice probably an element of En of the connected components. Well, I need more space. Let me just use again quickly. Yeah. So it's choice for all n of En, so that's a connected component of complement of each of these SNs. So pi 0 of sigma plus S1 such that, yeah, and then we want the actual like connected components to be ascending to. So Sn here, and then we also want E1 to be contained, E1 to contain E2, and so in this example, it would be something like you pick like this region as your E1, and then you'd pick you get to choose from these two connected components, And so let's say you pick this one as your E2, and so you just continue making those choices, and that would be an int. So this can be called a flip, a topologically distinct way of going on. More abstractly, and this is a definition that works like for any topological space, you can say that the ends of any space X, the end space is defined to be the inverse limit of these different discrete spaces pi 0 of sigma less s n, sigma less k, or I mean x less k, or k compact, and we want these to be ordered by the kind of like reverse inclusion. So each of the k's will like so okay we have a directed system of the compact subsets k, and those include into each other, and then when we take pi 0 of their complements, then that reverses the direction, and so we get an inverse system. So that's what I mean by that. But then going back to the kind of less abstract definition ends, then we now want to put a topology on these. We want to form the end space. And so the way that we do that is we say that the basis of the end space is we want the set of sets of E such that, and so like we'll say the E is like this sequence here. We want the set of sets of E's such that like EK is equal to some particular finite type subsurface S. And so like a basis element would be something like so there would be one basis element corresponding to each finite type subsurface, and that would contain as the points all of the ends which contain that finite type subsurface in their sequences.
Okay, so intuitively, is this saying that in the end space, points are close, like two ends are close together in the same open set, if they're kind of morally going off to infinity in kind of the same direction, because they agree on some EK, I guess.
It's like when you can put topology on the Cantor set. I think there's a name for this. I'm forgetting. Like an organic, like what this is called, but you put the topology on like sequences of 0, 1, such that like the basis elements on this for the Cantor set are like sequences which agree up to the nth term. So if like your first n terms are identical, then you're in some basis element associated to that.
I see. Good.
Yeah. So okay. So that is what the n space is. Yeah, and then outside of like infinite type surfaces, this also has applications. Like for example, this is apparently important in proper homotopy theory because a proper homotopy has to fix the ends pointwise. I don't know if that means anything to people here. But possibly, I don't know. I think you're saying homotopy theory will tell Greg that this is at least worth something. Okay, so hold on a minute. So I want to define non-pronouns. Let me just clean. Oh, this like the so this is going to be omega plus 1 in the order topology. So what this means is and so what this means is that you have a natural number's worth of discrete points. You have countably many discrete points, and then you have a single point, which is like accumulated by these. So you have a single point whose neighborhoods contain various infinite subsets of like the discrete of the punctures. And then another example would be something like this. If you had I want that, I want this, and then each of these is punctures going up it.
And the punctures accumulate in all of those branches in the same way?
Yeah. Okay. And so in this case, you'd have the end space. Okay, so these go up. In this case, the end space would be this one should be omega squared plus 1. I think that I'm just I'm just gonna remember how to like write this in like the order topology notation. Yeah, so you have is that right?
Sorry, what's the 1? I would have thought it's not omega squared plus 1, because the plus 1 in the top is the one guy that you're accumulating out to. Like, what is the one end in the omega squared plus 1? Because they're accumulating in different ways, right? Oh, the one on the right. Oh, good.
Yeah. So this one is accumulated by accumulated ends. It is it has a Cantor-Bendixson rank of 2. Is like something that you can that's like the formal way to say this. So we have like countably many ends which are accumulated by punctures, and then we have one end which is accumulated by ends accumulated by punctures.
Oh, I see. Okay, that's probably right then. Yeah, that makes sense.
Yeah. And then yeah. Okay. So this is how the end space works. Any other like questions about this? Okay. I trust that somebody again for people who haven't like who weren't there when I said this initially. I can't see the chat, so if you have a question, then you'll have to say it because otherwise I can't see it. Okay. So now I'm going to talk about ends accumulated by genus. So non-planar ends. So the end owner or accumulated by genus is each of the like the connected the connected components elements of the subsurfaces En uh, cannot be embedded in the plane. So the example would be um, also right, each neighborhood of this end, like this, would contain all of these handles, and as a result, it could not be embedded in R2. However, for the through surface, then a neighborhood would look something like this, and that would be like you could kind of imagine stretching it out, so pulling this orange part apart, and you get open disk like this, and it would have all of these punctures accumulating to some like big puncture. And so this is the subset of R2, and so this would be a planar M. So unplanar could be planar.
So is this definition like schematically distinguishing between handles and punctures? Because I would have thought they behave the same way, but this seems to be sensitive to the difference between them, right?
Right. So this is So this is what's allowing us to detect if your ends like. It turns out that the ends which are kind of accumulated by genus special, and they just behave differently than ends which are not, and so we want to be able to distinguish these. And so the reason for this is the following result. It's important for the classification, basically. But first, before we talk about that, I just want to say a few things about this topological space, the N space. So, N space, it's compact. It is totally disconnected. And it is metrizable.
Are these properties true for the n space of a general topological space using the definition with the inverse limit, or just for surfaces?
Nope, I'm just talking about surfaces.
Okay, good.
Although, that's a good question. I can probably get back to you on whether this is true in general. It might be. Nothing immediately comes to mind, but
okay. Yeah, anyway. It's not a big deal. It's just a random curiosity.
Yeah. Okay, and so this is compact because, like, I won't get proofs of these, but it's compact because, in a sense, you have to contain there is no way for ends to just continue going off and off and off without accumulating to something, and yeah, because like for example, you couldn't have something like you could not have something like omega, like the natural numbers, as your n space, as we discussed before, because the ends have to accumulate to something. Otherwise, you would have a point that's not Euclidean. And for this reason, it's like that's a heuristic argument. I won't give the proof of this, but that's like why you should at least believe that it's compact. It's totally disconnected, essentially, because you can always find finite type subsurfaces which will distinguish between your ends. And it's metrizable because it actually turns out that it is any n space of an infinite type surface, or just of a surface in general. Any n space is homeomorphic. I guess I'll more cleanly say any n space embeds in the Cantor set. And specifically, this is a closed domain.
So you say it inherits a metric from this embedding in the Cantor set? Is that the point?
Yep. Yep. So any n space, this is so yeah, and then you can make the stronger claim that any closed subset of the Cantor set is an n space of some infinite type surface, or of some surface. Any closed subset of C, or C, is the ends of something. And specifically, we can even construct it is the ends of the plane of the sphere, less that subset. So for subset S, S1, S2, S1. Any closed subset of the Cantor set is the end space of the surface obtained by subtracting that subset from the sphere. So this in particular proves that there are uncountably many infinite type surfaces because, well, maybe we haven't said this yet, but surfaces with different end space are not homeomorphic, and so there are uncountably many closed subsets of the Cantor set of the homeomorphism, and this proves that result. And this is kind of surprising, I think. Like, at least when I first heard this, then just did it like it's always like it just makes me think like the Cantor set is just kind of a fundamental object. Then all we have like all we have the only information we have is just that these are Hausdorff second countable locally Euclidean spaces, and it just turns out that the number of ways to go to the space of ways to go to infinity happens to be a subset of this thing, the Cantor set. So
Yeah,
I think that's kind of cool.
I find it surprising as well because usually you learn about the Cantor set in some analysis or topology context as like this weird thing you can do, this kind of pathological example. But here it's actually a quite natural geometric object in some sense, right?
Mm-hmm. Mm-hmm. And speaking of natural geometric objects, the realization of this is that because I haven't said this yet, but the end space of the Cantor the end space of the Cantor tree is the Cantor set. And so you can actually take any infinite type surface, provided that its ends are not accumulated by genus, and embed it into the Cantor tree as a subsurface. And you can do this in a way that corresponds to the embedding of the end space to the Cantor set. So, so I guess I'll write that. Any no non-planar ends. Planar ends embeds into that. Okay. Any questions on this? Oh, okay. Okay, so now I will discuss the classification. So Ian Richards proved that infinite type surface is determined by the following triple theorem. The genus, which can be any number or infinity, the end space, and the subspace of the closed subspace consisting of non-planar ends. So if you so if you know these two values, then you know the surface. And also, if you have a choice of G and N's and N's accumulated by genus which align, then any homeomorphism between like the N spaces corresponds to a homeomorphism of surfaces. So, yeah. So that's kind of the end of the like just generally about infinite type surfaces part of this talk. That went a little longer than I expected, but it's fine. And now I'm going to go a little faster just to I know some people here are just interested in hearing about research, and so I'm going to talk about the flip graph and the mapping cost group and the Ivanov-Matic conjecture. That concludes the first half of the talk. Thank you for coming. Anyway, so here's what I'm working on. So the flip graph is and its edges are these kinds of things. They are flips, and they look like this. So you take your triangulation that looks like that, and you flip it, it looks like this. Like this. Flip.
Wait, sorry, there's an edge between two distinct triangulations if related by this kind of symmetry operation? Is that the statement?
Yep. If they are related by a flip, then
okay.
They're aesthetically adjacent in the flip. So this object has been studied for finite surfaces kind of a lot. It's also known as the triangulation graph. Little help with it. It is a so there's like a couple of good results about it. So first, it determines the surface. So we have like a homeomorphism between one, zero, x, and 2. Then that gives rise to a map of surfaces, so long as f is injective. And if f is like a graph isomorphism, then this is a homeomorphism. So this is injective. Then we get this. And this corresponds to
one-to-one correspondence, or you're saying that just given a graph homomorphism of flip graphs, you can construct this map between the surfaces?
So you want an injective homomorphism graphs, but yes, then you can. Is it a one-to-one correspondence? Well, any like map of surfaces, okay. So if you have a homeomorphism of surfaces, then you get a isomorphism of flip graphs. And this is because if you have a triangulation of one surface, and then you you homeomorph it onto another surface, then you get a triangulation of the second surface. And so that's one direction. And then this theorem is saying that you can go the other direction as well. So for isomorphisms, it is a one-to-one correspondence. For injective maps, it's not, because if you merely include like one surface into another, then there are many ways to like complete the triangulation of the instance.
I see.
Yeah, so I guess one thing I should say is that we are talking about ideal triangulations here. So, for example, it would be something like we want our arcs to connect. So we have, I don't know, what's a good surface to triangulate? I'll just do the flute for now. We have these functions, Then the triangulation is going to consist only of connect ends. Actually, when anyway, we're allowed to have ones going on infinite ends. Okay, so this equals to case. And for phenotype surfaces, it determines the surface. Um, it works well with homeomorphisms. And it's also like asymmetric. This stuff I don't know as much about, but as a metric space, I am told that it is it's like infinite diameter. It is Gromov hyperbolic, whatever that means. It has these nice properties that make it, in some sense, analogous to Tekmolo space, and the way that the Mathicos group, I should explain that. So, MCG, sigma is the extended Mathicos group, is the homeomorphisms of sigma, like just, from sigma to sigma, modulo isotopy. And so this acts on the hook graph. Just by taking a triangulation and doing something to it. So if we have triangulation of the flute, and then we do homeomorphism, which consists of like twisting along a certain curve. No, I won't draw it. But yeah, so the Navigas group has a photograph, and it turns out it acts fully faithfully for phenotype surfaces. The symmetries of the surface are exactly the symmetries of the photograph. Automorphism group of the photograph is isomorphic to the, like not so isomorphic to the Navigas group. Finite type surfaces. And so for infinite type surfaces, the result that we got in my group of collaborators was that it acts faithfully, but there are some there are some graph isomorphisms. There are some automorphisms of the float graph which are not induced by homeomorphisms of the surface. So you can say, the last group sigma is a proper subgroup of the automorphisms of the float graph.
Sorry, it was cutting out a little bit, but just to clarify, you said this was your theorem, so this is the new result. Is that the right?
Yes.
Good.
Yes. And then there's a different new result that I'm sorry, I don't have a lot of time for this. I want to leave at least a few minutes just to cover the application. you mentioned, well, ready to go. And like, that's all, I guess. Then I'm going to say I'll take questions, but then I want to hear about this, like the thing you said last time that I was not privy to, and that involves.
Oh yeah, the discussion
I think it's correct.
when you dropped
Yeah,
out. So
yeah.
yeah, I mean, yeah, I could talk about that, but I don't want to monopolize. So if there's questions from the from other people, since I've already monopolized the questions so far, so definitely other people ask first. Okay, maybe there's none. So
Okay.
uh, okay, so this is actually very interesting for a totally different reason to me. So um, I'll give you an example. This example might you certainly know this, but for other people, this might be a good piece of intuition for the mapping class group. So when we had that improvised talk I gave on modular forms and the torus, so the mapping class group of the torus is basically this SL2Z, this modular group, um, and that occurred in that context of that talk because I was talking about string theory, and in string theory, the worldsheet path integral instructs us to sum over all surfaces because the worldsheet is two-dimensional. So the worldsheet can take whatever surface it wants. And in some sense, if you're familiar with ordinary point particle quantum mechanics, this is analogous to when you do the path integral for a particle. You integrate over all possible paths that the particle can take. And even though the classical path, which solves the equations of motion in that context, is always, smooth, it's like a, nice differentiable curve or something like that, you can prove that such smooth curves are a set of measure zero in the measure induced by the path integral, because a generic path will have discontinuities in various derivatives because it'll be jagged, basically. It'll look like some Brownian or some Wiener path or something, some random thing. So in point particle quantum mechanics, the point is the space of paths you integrate over is wild. Generically, the paths in that space have no nice properties, but they average out in some sense to nice smooth paths or something. So I think there's probably some analogous story here. I've never seen this discussed, but in the string theory path integral, we're summing over all surfaces. And if there is a sense in which infinite type surfaces are somehow generic in some measure on the space of of surfaces, then it's probably the case that most contributions to the string theory path integral are from infinite type surfaces of this form. But to make that precise, the statement you said that the finite type surfaces up to maybe homeomorphism or something are countable and these things are uncountable. So that statement about cardinality is not quite enough to make this statement that I said precise, because in addition to cardinality, there's some moduli space volume. There's some integral. So for the torus, for instance, there's one Teichmuller parameter, which is basically tau, the complex structure of the torus, which sits in this mapping class group. So when you compute the contribution to the string theory path integral from the torus, you need to integrate over its moduli space, or essentially over its Teichmuller space up to some identifications, which, I'm being a little imprecise. The Teichmuller space of the torus is the upper half plane. So it's really the mapping class group where you impose this symmetry, which comes from basically the SL2Z or something. So I was kind of interested in how much was known about the mapping class groups or the Teichmuller spaces of these infinite type surfaces, because it could be that if you could do these integrals over these moduli spaces, essentially, for these infinite type surfaces, that one could show that, look, uh, your intuition from string perturbation theory is not quite correct. Because if you tell an average string theorist, oh, look, there's these infinite type surfaces, they would say, oh, I don't really care, because in my string theory path integral, there's a factor of e to the minus integral root gr. And for a nice smooth manifold, the integral of root gr by Gauss-Bonnet is just the genus. So e to the minus genus appears in front of my integrals. So these things are massively suppressed at large genus. They would say, oh, look, e to the minus genus, it's going to kill you. These things don't contribute at all. But maybe what you should have said is like, okay, sure, there's an exponential damping factor, but there's also a measure. And it might just be that the measure of these surfaces is so much larger the measure of the small genus surface is that it's beating this exponential, and these things are somehow contributing. So that was I wouldn't call it an application. That was the wild speculation that we were talking about last time after the preview um, with Odium and friends. But
That's really interesting to hear. That's I, why are they like? Why are the spaces that we're concerned with in this case surfaces? Why are they manifolds of dimension 2 exactly?
oh, right. Yeah, it's because the string, if you think about a string propagating in space-time, so this is, I mean, it's really a Lorentzian two-dimensional space. So if you have a string moving in space-time, just imagine a graph, like a three-dimensional plot of where the string is at each point in time. So the vertical axis in this plot is time. So each slice at each fixed time, the string is one-dimensional, one space dimension, but it traces out as it propagates through time. Just imagine the string kind of moving upwards and tracing out a curtain in the vertical
Yeah,
direction, which is time. So this is a two-dimensional. This is called the world sheet. So in string theory, the world sheet is two-dimensional, one space and one time. So without doing any additional tricks, you would say, okay, well that does not apply because that is not a Riemannian manifold because you have one space and one time direction, and time does not behave like space. So that is not a surface. But then I tell you, oh, okay, but I mean, when we do string theory, we usually do a Wick rotation. So you reparameterize time. You send t to I tau, basically. So you go to imaginary time, which makes it Euclidean because now the minus sign in the metric gets flipped by this I. So essentially in string theory, what we're really doing under the hood is analytically continuing all things that you compute to complex time because it makes the math easier to do the integrals. So if you do that, then the string world sheet is now a two-dimensional um, Riemannian. It's a perfectly ordinary manifold because space now, or time now acts in a Euclidean way. So your two dimensions are time and the one spatial dimension along the string. So that's why surfaces naturally emerge. So two dimensions is very special in string theory, and basically all perturbative string theory calculations boiled down to analysis of surfaces. Like for the closed string, the torus, computing the torus partition function is essentially what gives you the space-time Einstein equation. For an open string, we typically do the disk. For unoriented strings like type 1, you do integrals over like Klein bottles and things like that. It's all
wow.
surfaces.
That's that's cool. That's like yeah. It's interesting that like such a kind of I don't want to say classical because that's like I don't like the way that word is used, but it's like these are like examples in undergraduate topology classes, and it's like it's interesting and cool and encouraging that that those surfaces are actually like what you're calculating with as a string theorist. So
Yeah, it emerges in a very natural way. I agree. It's encouraging because sometimes, I mean, in an undergraduate math curriculum, sometimes things can feel unmotivated. But if you just open up greenshortsweden and page through it, you will see like it's basically a tour of various things from undergraduate mathematics. Like Gauss-Bonnet theorem, as I said, emerges in a natural way. All these surfaces emerge in a natural way. Group theory and homology and homotopy emerge in a natural way when you're kind of classifying certain aspects of these world sheet constructions. So anyway, yeah, it's interesting. It was a long walk and it's a diversion from what you're really talking about because I mean it's it's not clear, I guess, how you would do calculations that contribute to the world sheet path integral from these infinite type surfaces without a really good analytic control over what the mapping class groups are. It seems like my impression from what you're saying is that the mapping class groups of these objects, I mean, you can make statements about embeddings of them, or you can make general statements about the properties of the mapping class groups, but they're not explicitly known where you can write them down, except maybe in some nice
yeah,
examples.
yeah. There. I mean, even for finite type surfaces, then the mapping, at least as I understand it, except for some simple surfaces like the torus, like if you take like the genus 10 surface, my understanding is that the mapping class group is um, something weird. It's something like it does not really have a concise way of writing it besides the mapping class group of the genus 10 surface.
Yeah, oh, that's true. That's true. Yeah, even well, for the same reason we typically don't compute with those because that e to the minus 10 then enters. So yeah, I agree.
Yeah.
Yeah, they're not known there, but I mean, in some sense, I would say, oh, it may be true that even though it's not known for genus 10 and it's not known for infinite type surfaces, that in some sense I should care more about the fact that it's not known for the infinite type surfaces because they might have this measure factor appearing. Because
Of
like,
course, yeah.
yeah,
Yeah, that's really cool. I have to go now. My school day is about to end, so I'm about to be kicked out. But this is fun. Thank you. I'll
yeah. Thanks for the talk. This was fun.